our history goes back to developing with the cooperation of Tyndall in Cork, a company called InfiniLED, which we sold to Meta. So microLEDs started in Cork, Ireland, in a sense. And thanks to Tyndall, the patent came out of Tyndall. We developed it. These were integrated microLED with parabolas inside. And that company is still under Meta in Cork, Ireland. So because of that knowledge and expertise, we realized there were limitations to what microLEDs could do, especially in terms of display. And after 8 years or 10 years of microLED development, we still have those challenges left in commercializing microLEDs in a large way, although some new products are coming out. So at that time, we decided to go into nano-LEDs and make them 1,000 times smaller. The advantage of micro-LEDs, of nano-LEDs, let me see.
I think it works. It is on.
Oh, no, it's wrong. Is to do nano-LEDs using molecular beam epitaxy. The fundamental advantages of MBE, and I'll tell you what the disadvantages are in a moment, is of course that it is physics, not chemistry. That fundamental changes the paradigm. If you want to change something, you have to change the paradigm. So in physics, you don't have the leftover particles of the precursors in a MOCVD system or any other system. You don't have impurities. And above all, you do not have dislocations. There are no dislocations in our structures. So gallium nitride nano-columns we make, there are no discontinuities, none. As the diameter of the nano-column goes smaller, our EQE increases, not decreases. And then, of course, you have to have the device capabilities to take most of the light and get it out of there. For that, we have some advanced P contacts, which increase the EQE by about 15%, just because of the P contact and its structure and the process by which we do it. Now, of course, the systems are simpler, but the main reason why they have not been commercialized yet are MBEs are difficult to calibrate, sometimes 10 days, 20 days, 4 weeks. Wafer temperature cannot be read because the vacuum is so high, you cannot put anything inside to detect the temperature. You can read the temperature of the heater, but not the wafer. And that could be off by 250 degrees on a 1,000 degree C operation. So there are limitations. There are no simulation tools to actually see what conditions control the structure so you get pure Wurtzit crystals, hexagonal with a pyramid at the top, which means C-plane, which means no defects. And of course, there are no large-scale lithographic tools. For large volume, there are, ASML, of course, being the best, and others, but in small volume, there's none. So doing every wafer by E-beam takes a long time. So that, luckily, we have resolved all these issues. So we have a non-contact temperature reader. We have simulation tools, which this talk is about, which is computing physics. And we have reduced the time from 6 months of computing to 5 days. Apart from that, we can capture the snapshots of the simulation so we can present you a video in a minute. But that tells you exactly what temperature, what flux of nitration, what flux of gallium, and what flux of indium you need to get a proper crystal and the proper indium content in the quantum wells. So we can simulate a quantum well. And of course, we have nano-imprinting replicators. So if you have the master on E-beam, you can replicate the pattern.